Hello everyone and welcome to our channel. Today we are going to discuss the question flood field. So in my opinion, this is one of the most important questions related to the concept of backtracking and recursion in general. So this question has been asked a lot of time in a lot of companies like Amazon. So I'm going to discuss the question in a lot of detail. So this video might be a bit lengthy, and I will try to not make it boring and make it a bit engaging. So just I will request everyone to be patient with the solution, okay? Because I'm going to discuss step by step, okay? So let us proceed further without wasting any time. So before discussing the question, I will just quickly want to remind everyone the concept behind this. So the concept behind this question is called as backtracking, okay? What is backtracking? Backtracking is a method of finding all possible solutions to a given question. All possible solutions, not question. All possible solutions. So how is it different from other method? So in lot of methods like dynamic programming or greedy method, we will use we have not studied that till now, but in the further lectures you will study about dynamic programming where we find optimal solutions, where optimal solutions give the best possible answer. But in backtracking, we don't use the method to find an optimal solutions. We use backtracking to find all possible solutions. Solutions like if we are asked to print path from start to end, and we want to print all possible paths, not the path with the like for example lowest cost or something like that, but paths, all possible paths. Okay, so for that thing we use backtracking. So just a quick example. For example, if we are given a board or basically a wall, just a wall, and there are three parts of it, and we have been given three colors: blue, red, and green. Okay, now we are asked to print this wall. So how many different methods of printing this wall? Since there are three places and there are three different colors, so we can print this wall in factorial three methods. So there can be six methods. Okay, now how how to find this method? There can be several ways. So I'm going to find these combinations using backtracking. So this should make the concept of backtracking a bit clearer. Okay, so let us start by painting this as red. Painting the first one as red. So I painted the first one as red. Now I have option to paint the second one as blue or green. Let us just paint it as blue. Now the last one, this one, I have only options of painting this as green because only one color is remaining. So I paint this as green. Okay. Now what we can do is we have already found one of the solutions, but this is not it. We have to find all possible solutions. Okay. So what we do is we backtrack, that is we move backward and we check at this point is any other solutions are possible. We have used blue here, so is there any other possible solution? Yes, there is. We can use green here. So what we do is we remove these two nodes and we add here green, and the last one would be blue. So we have made two different solutions. Okay, now if we move further, if we move backtrack again, we do drag tracking again, we see that we have exhausted all possible solutions because we have already used red here. So we have remaining options is blue and green, and we have used blue and green here. So there are no further possible solutions. So what we can do is we can backtrack further also. If we reach here, we have options to paint the first column as either green or blue. So we can have more solutions. So starting from green, we can paint the second one as red, the last one as blue. Similarly, we can paint the second one as blue and the last one as red. Now if we start from blue itself, so we can paint the second one as green, we can paint the last one as red, and we can paint the second one as red and last one as green. So we have found all possible six solutions here. This is how we use backtracking to find all possible solutions. I hope I will being clear. So this is what we are going to use in this question and in coming up questions. So I want everyone to clearly understand this concept. So now what I'm going to do is discuss the question that we are provided with. So the question is called as flood field. Okay. Now what I'm going to do is I'm going to make a 2D array. Okay, so I've already made a 2D array to save time. So this is the 2D array. Okay. Now the question wants us to print. The question is stating that we are here, standing here. Okay, this is the top left corner. So let us just quickly uh, index these rows and columns. So 0, 1, 2, 3, 6. Okay. So the question wants us to start from here and reach this block. This is the end position. This is the start position, and we have to print all possible paths that we took to start from here and reach here. What I mean by saying that is that we have to print all possible paths that we followed while starting from here and reaching here. So we have been provided with certain constraints, like there are only 4 possible movements allowed. They are in the order of top, that this is one step up, that is in this direction. This is now the next one is this one is L, that is one step left, that is in this direction. This is one step, the next one is one step down, and the last movement is one step to the right. So in this direction. Okay, so up, left, bottom, and right. Okay, now since we have only these 4 movements allowed, we can't move diagonally or any other movements allowed. So let us just quickly, by visualizing it, let us just try to find a path. Okay, so if we are here, what we can do is we can move downwards, then we can move here, then we see that we can move right also. Now before and finding ways, I forgot to mention one thing, is that this matrix is filled of zeros and ones. Okay, so the blocks which are empty are actually filled with 0. Okay, and the blocks which have containing 1 are obviously filled with 1. So the question says us that we can only move in the blocks, through the blocks which are filled with 0. We can't move through the blocks which are 1. So this basically, the block containing 1 is an obstacle. We can't move through it. Okay, so there can't be any path which is moving through them. So we have to consider that in our mind also. Okay, so now we start moving. So we can move down. We see that there is a block here, there is a obstacle here, so we can move here. Now we move right, we can move down here, and we can move to the right. We move down, then we can move to the right, and we reach our destination. Now there can be more solutions like this one. For example, if we move down, we keep moving to the right. Now we move down, and now we reach here. Now there can be one more solution. That is when we start moving here, move here, and instead of going in the same direction, we move up here, then we go here, then we move down. We start here, go here, go there. We move down, we move to the left, we move down, and we reach here. So these are the 3 possible solutions for this particular matrix. Okay, this particular maze. Now we are required to print the path, not actually find the number of paths, but actually print the path. Okay, so what we can observe from here is that we started moving. If we, let us just write the path for the green line. Okay, so we started here. Okay, so what we did was we moved one step down, so we can write D here. Then we move one step down again. Let me just write it in green. So we move one step down, so I write D here. We move one step down again, so I write D here again. Now we move one step right. I will write R. then we moved 3 steps down. So I let read three times. Now I moved 1 2 3 4 5 5 steps to the right, and after doing this I reach our destination. 1 2 3 4 5. Okay, so this is one of the possible paths. Now we have to write print paths for all possible solutions. So this is basically our question, and I hope everyone understood that. So now what we are going to do is we are going to write and we are going to code, and I'm going to explain along with the code how to proceed further. So this would be much clearer if I explain along with the code. Okay, so the first thing is the basic thing that we understood is that we are allowed to move in 4 directions, so we'll make recursive calls in those 4 directions. So let us just see, if we are on 1 step to the up, what is what changes would we do? We are moving only 1 step up, so we are decreasing the row by 1. So if we are at SR, this is our current row, and SC is our current column. This is our current row, this is our current column position. Okay, so if we are SR, if we move 1 step up, this would be SR minus 1. Okay, if we move 1 step to the left, we are decreasing the column, so this would be SC minus 1. Okay. If we move 1 step down, this would be SR plus 1, because we are increasing the row, and similarly SR plus 1, and similarly this would be, we move 1 step to the right, this would be SC plus 1. Now all we have to do is make 4 recursive calls displaying these 4 changes. Okay, so I'm going to quickly write that here. We're going to pass, and we are going to use SR plus 1, not plus 1. So first one should be up, so SR minus 1, SC, and answer so far. So one thing that we are going to do is throughout the code is we are going to maintain this order TLDR, so it would be more like a homogeneous solution. So the next thing is I already moved top, so next would be TL, so it would be L left, so SC minus 1. Now not SE here the SR would remain same, the row will remain same, only the column would change. So SC minus 1 and SR so far. Now we are moving TLD, so we are moving 1 step down, so I will increase the row SR plus 1. Now I'm moving 1 step to the no, the SC will remain same because we are only checking the row. The last one will just increase the column by 1 because we are moving 1 step to the right. Okay, now one thing that we have to keep in mind is that we are making blind calls, so we can say that these are not intelligent calls, because these calls are just to move along, just to traverse. The main like what can you say, the smart thing that is to be done are will be done by the base cases themselves. Okay, so the base cases that we have to write should be smart, that is they should handle all the edge cases. What are the edge cases here? So as you can see in the first block here, so we are only allowed to like if we first as we can see, the first step here is T. Let me just start over. Okay, so in the first column, in the first block, we are allowed these 4 movements. So if we try to move to the 1 step up, actually here we move outside of the maze, so this movement is not allowed. So as I explained earlier, our calls are not smart calls, so we have to make a smart base cases so that they can handle all the edge cases or the cases which are not valid. So we have to consider all those cases, and we will write a base case for that. So if SR is less than 0, that is if we try to move upwards and we move outside of the matrix. Now next one is SC is less than 0, that is if we try to move left direction and the column is less than 0. And if SR is equal to array dot, not array, should be maze dot length, that is if we try to move in the downward direction and we reach to the edge of the maze, and if SC is equal to maze 0 dot length, that is if we move to the right and we reach the edge of the column. So if these four conditions are encountered, we will not do nothing but return. Okay, so this will handle all the cases where move outside the maze. Now there is one more edge case here. So as I explained earlier, not only these four, we can also move to the blocks which contain one. So we also have to handle that. Okay, now just quickly write that here. What I will do is I will write maze SR SC is equal to 1. If we encounter a 1, we'll just return from there. Nothing special about it. But one thing that you have to like everyone watching this should have to understand is that why I wrote maze after these four calls. So if I had written this in the first step here, so this would have encountered situations where the SR or SC would not have been valid. For example, for SR less than 0, that if, for example, if we take SR minus 1, so it would have encountered conditions where maze minus 1 and some SC would have been checked as is equal to 1. So what I'm trying to say is that for if I wrote that in the first, so it would encounter conditions like this. So for example, maze minus 1 5, something like this. Okay, so this actually will cause an error. So we don't want a situation like that. So we can only want valid values of SR and SC. And how we get the valid values of SR and SC is all the values which are besides these four conditions are valid for SRSC. Okay, so the SRSC which is here is already valid because we have already checked these four conditions. Okay, so we don't need to check them again. So these SRSC are already valid. That is why I have written them here, because if any one of them is true, they will return. So this SRSC is already valid. So this is why I wrote it in the end. Okay, now I've written the whole code. So at first glance, it seems that I have done all the tasks, but one thing is that actually I have left it. So I will write it. When we read to the destination, what is the destination? It is basically this point. So this point is our destination. So what is this? This is basically here it is 5 comma 6. Okay. So this is array dot length minus 1, and this is array 0 dot length minus 1. Okay, so I will write this here. If SR is equal to, here array is maze, so I will write maze dot length, and not or and both should be true. SRSC is equal to maze 0 dot length. Okay, what if we encounter this condition? We will print the answer so far. While writing this, I am observing that I have made one mistake too, so I'll just fix that after writing this. So I'll print answer so far and I will return from here. So the mistake that I made was I haven't updated the answer so far. So one thing that we have to do along apart from moving is that I have to update the answer so far after every move. Okay, so if we move one step to the top, I have to add T here. Okay, T for top, L for left, D for down, and R for right. Okay, similarly this is for one step to the left, so L. This is one step to the down, that is D, and finally this one is one step to the right. This is, I'm going to increase the font size so it is more visible. Yeah, now this is clear. Now if I run this code only, this would give me Stack Overflow. Why? because this solution will run infinitely. Why is that? I'm going to explain that here. So let us just consider this. So I'm going to go back to get the fresh maze. Okay, stay with me here just a minute. Okay, now since we have an empty mesh, now we can proceed. So as let us just follow our code here. Let me bring this code here. Okay, so I will just bring that code to the board. Decrease its size. Will just be a minute. Decrease a bit more. Okay, it's fine. So let us just analyze this code. Let us just follow these calls and see how the solution is being formed. So okay, now the first call is to move decrease the row by one. If we are here, if we try to move upwards, what will happen? It will see this condition as SR is less than 1, since SR will become -1. So if this happens, it will return. So this call is not valid, so it will return from here. We can't move in that direction. Similarly, or if we try to move left, it would become SC would become less than 0, so it will return from here. The base cases are handling everything. So that is why we should always write smart base cases, so that they can handle all the edge cases. So here they handled the both of these conditions. Now we are allowed to move one step down. Okay, because there is no obstacle there, or and we are staying in the maze itself. So let's just say we move one step down. Now again, if we see that here the call of moving to the top can be executed again, because we can move upside because we are inside the maze, and plus we don't have any condition which prevents us to move here, because this is not 1, this is equal to 0, and this is inside the maze, so we are allowed to move here, so we'll again move here. Okay, now if we are here again, then again the same calls will be executed. It would again make me reach here. Here again the same thing will happen. It will again make me reach here. So as we can see, this call will get executed again and again. It will never stop, because there isn't a condition which prevents that from happening. So what we have to do is we have to uh, somehow prevent the recursive call to make the call for that cell that we have visited already. So what I'm trying to say is that we have to somehow mark this block as, what can you say, as visited, and we don't want to visit this cell again, so that we don't have to make repetitive calls. Okay, so how do I do that? I will just take a boolean array. Okay, so I will make a boolean 2D array of the same size as the array that is the maze. So I will name it visited, because we are checking if the cell is visited or not. So I will make this, the size would be n. I will just pass this in the function call, and let me move this here. Okay, okay. Now I will just write string boolean and visited. Now what I'm going to do is I'm going to pass the visited in all of the function calls. So it's getting a bit congested, so let me just copy paste the code in the editor. So we have more space there. Okay, so let me just copy paste the code here, and let me just move this to the right. Okay, and the code should be clearly visible. Now what I was doing is I was passing this visited. Okay, I pass this visited here and here. Now what I wanted to do is using this visited, what I'm going to do is I will mark those cells which I have already made calls on as visited. So I will just mark a virtual tick on them. So how do I do that? I will just, after this I will make the current visited for the current block. Current block would be srsc. I will make visited srsc as true, and I will add a check here. If visited srsc is equal to 1 true, it will return. So what this will do is that if a certain block is already visited, it won't visit it again. How? Because let's just see here. If first I started from this, then before making the recursive calls, I will just delete this and I will delete this, and I will now take this to the board. Okay, so we just decrease the size. And bit more. So okay, now as we can see in this code, before making the calls here, as you see that before making the recursive calls, I am marking the cell as true, marking the visit as true. So this would actually mark this as true, the visited. And if we in the step that in if we move after the recursive call, as I discussed earlier, we only have options to move downward. So we will move here, and if we try to move up again, it would check that this visited srsc is true, so it will return from here. So we won't have the problem anymore, because if we try to move upward, it will check if visited srsc is true. It is true, so it will return from here, so we can make the upwards call. Now if we proceed forward, if we try to make a left call, this is not possible because it will move outside the matrix. So the only now we can only move forward, so that is we can have we we can move to the down. Okay, so let me just start from the beginning, and I'm going to explain from the whole path. Okay, so stay with me here. It is going to be a bit redundant, but dry running a code is very important. It is the one of the most important part while trying to become a expert programmer. So you should know how to dry run it. So let me just start it. So we start from this cell. Okay, we checked if we can move left. Here we can move left. This is for moving not left but up. This is for moving left. This is for moving to down, and this is for moving to right. So we first check if we can move up. We can, because it will take us outside the matrix. Similarly, for moving left, it will take us outside the matrix, so we can only move down here. because down is the next call after these two, so we move down. Now if we try to move up, before moving down we mark it as visited. Actually we marked it and visited before making the calls itself, so it will be marked visited already. So now here we check all these conditions, so we see that visited SRSC is true, so we return here, so we can't make the up call. So we check the left call can't be made because it will take us outside the matrix. Now to the decall can be made, it is possible, it is a valid solution. We will move here. Okay, this will mark it visited. uh the actually will mark the block visited before making these calls. Okay, so as soon as we reach the block we'll mark it as visited because this is before all the calls. So as soon as we reach here we'll mark the call, we'll mark the block as visited. Okay, now we'll make the call. So we check, can we move up? We can't because it is visited. Can we move left? We can't because it will take us outside the maze. Can we move down? We can because this is one here. We can't move to the cell because we already uh, wrote a condition here. It will return us. So we'll move to the right. Okay. Now what will happen is that we'll check here. Can we move to the uh, we'll make all these calls again. So before making calls it will mark it visited. Can we move up? We can this is the one. Can we move left? We can because it is already visited. So we can move down, we'll move down, mark it as visited. Again the same thing, can't move up, can't move left, but we can move down, we'll mark it as visited. Same thing again, we can only move down because there is one to the left, there is switch to the right, to the upwards, and we can only move down, so we'll mark it as visited. Now we'll check, can we move up? No, we can, there is visited. Can we move left? There is one, we can't. So we move down? We can't because it will take us outside the matrix. Okay, so here we have only one option of moving to the right. So we move to the right and it will mark it visited. Okay, now we move to the right, it will mark it as visited. We move to the right, it will mark as visited. I skipped this test because no further solution happened because we can't move up, we can't move down, we can't move to the left because all of them are visited. So we only have only one possible movement in these cases is to move right. Now when we reach here, we see that we have options to move to the up because it is not visited, not one, and it is inside the matrix. So we move to the up, mark it as visited. We move to the up, we mark it as visited. Now I'm going to speed it up a little bit. I'm going to go here. Okay, now the next call we can move left, we can move to the right, as you can see from, but the next call is for left, so we will move left. We can move up because there is one. Okay, so we move to the left, it is visited. We move to the left, mark it as visited. We move to the up, mark it as visited. We move up again, mark it as visited. We can't move left, we can move up, we can only move to we can move down, we can only move to the right. So we mark it as visited. We can only move right, mark it as visited. Move right, mark it as visited. Move right and mark it as visited. Now here we can move to the up, we can move to the left, we can move to the down, so we will move down, mark it as left, mark it as visited. We can again mark it as visited, and then finally we move to the left, we can move to down, we can move to the up, we can only move to the, sorry, we can't move to up because it is visited. We can only move to left. So if we move left here, so we move to the mark it as visited. So as we can see here, we reach to the position where no further movements are possible. So if this condition arises, we can't do anything, but all the functions have been exhausted. So we only have options to return here. So we will just move backwards. Okay, so I will erase them one by one. We'll move backwards. We'll 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 reach here. Okay, so here, as we did earlier, we made a call for top, we can't because it is visited. We made a call we made a call to the left, we checked already, so it is marked as visited. Now we also have to make two more calls, that is for the D and to the R. If we check for down, we can't because it is one, and if we make call for the right, we can't because it is outside the matrix. So no further calls can be made. So this is the same for all of these movements. Okay, you can check them by yourselves, but this will be same, because let us just say for this one, the right one is already visited, the upward can't be visited because it after the maze, the bottom one is one and the left one is visited, so no further movements allowed. So only option is to return from here. But just remember one thing, that these blocks are still visited. Okay, this is one of the most important part I want everyone to focus on, that these cells are still visited, because we have not written any code to change this block whatsoever. So let me just quickly return here. So I will return till here because no other movements are allowed. Now here I've already exhausted the upward movement because it is visited. Now what I can do is I can move. No, um, before proceeding that, now here, as I explained earlier, before we were going in this direction, that we have options to move to the left or to the right. Okay, but since we are making calls in an order, we moved left to left further. Now if we check here, we can't move to the right because these cells are already visited. So we are actually eliminating paths. Our question wants us to print all the paths, but we have eliminated the paths because we have made it visited. So we can traverse in this direction. But there might be a solution which wants us to travel in direction. So this is not the right code. We have to make some change. That is, if all the calls are have been made and no further solutions are possible, we'll mark the cell as as unvisited. What I mean by saying that is that if all the calls have been executed, we'll mark the cell as unvisited, so that for different paths, just that cell can be considered. So that what this will do is, while returning, this will actually make these cells as not visited. So we have the option to traverse these cells also. Okay, so these cells are all not visited. Okay, now here I've already made the calls to the left. I've already uh, calls to the left, and I can't move to down because they are visited, and I can only move to the right. So we'll move to the right. Same thing, we'll mark it visited, we'll mark this as visited. We'll move to the right, we'll mark this as visited. We'll move to the up, we'll mark this as visited. We'll move to the up, we'll mark this as visited. I move to the left, mark this as visited. The same thing. I don't want to waste time by explaining the same thing again and again. So we will move to the left, make this as visited, move to the left, make this as visited, move to the down, make this as visited, move to the down, make this as visited, move to the right, make to the visited. Now we again reach to the point there. We can't move in this direction. We don't have any solutions. So we'll move back again. So what I'm doing is I'm going to just undo it quickly. So we don't have any possible solutions in this direction. Okay. So what I'm going to do is I'm going to return from here. Okay, so I'm going to return from here. Okay, so okay, so what I'm going to do is I'm going to return from here, and I'm going to make them unvisited. But this just won't be visited again. I want everyone to understand this thing, that if I make this cells doesn't unvisited, doesn't mean they will be executed again, because we have already traversed in this direction. So this call has already been made because we are moving up. So this call has already been made. We have been moved past this call. So we don't want have to worry about that. What if I make this not visited, and What is I make this unvisited and it moves in direction again, it will do the same thing again. This won't happen because the this call has already been executed and it won't execute again. Okay, so we don't have to worry about that. Now all we have to do is check here. We have already moved to the upwards call. Upward call already been executed. Now we have 3 calls left. Can we move to the left? We can't because they are visited. Can we move to the down? We can't because it will take us outside the matrix. We can only move to the right. So we'll move to the right, mark it as visited, and move to the right, mark it as, and finally we have a solution where we reach to the end. I hope this dry run was clear. I tried to move step by step. So this code will have one more thing, as here we will write visited srsc as false. So the code itself is very short. It's very small, like very few lines of codes, but the logic behind this, it's very interesting and very important to know. Okay, so now the only thing that is remaining is for us to run this code. So let me just take this to the compiler. So flood fill, I will copy paste it here and run it. Oh, okay, so I think I forgot. Yes, uh, like one, I think I did not copy it properly. Did I? Let me just verify it. 1 minute. So I'm printing. We already made the call, so why isn't it printing? I think there might be some kind of. Let me just run it again. It isn't giving any answer. So I've added the SRC to SRC1. If SR is equal to minutes dot length. Okay. So here I have to write -1, right? Else it won't have it. There was a human error. Okay. As you can see, it has printed the part RDDR. So now I'll submit it and check if our code is completely correct. So this code is complete. All the test cases have passed successfully, and this is how we solve this question. I hope my dry run was clear. And the logic behind is pretty simple. We explored all the possible solutions. It is not the only path. There will be further 2 more paths, but I think you should try that by yourselves. That would help everyone to understand how we dry run this. So I'll just leave that there, and I hope my explanation was clear. So if you like the video, please don't forget to like and share the video, and subscribe for further contents like this, and I'll see you guys in the next video. Thank you.